Hey everyone, this is Muhammad.nadeem and welcome to my YouTube channel. Today in this video, we will discuss the topic which is present here, temperature coefficient of resistance or resistivity. Let's derive the expression for this, and then after deriving the expression, then we will explore the term associated with that expression. For derivation of the expression, we have to consider a rod of material. Here in this case, this is the copper. This rod is actually made up of the copper, therefore we call this rod as a copper rod, and we consider this copper rod. And this copper rod will present in some environment, and that environment will have some temperature. So in this case, the temperature of the environment, let's say 25 degrees centigrade, and this will be the temperature of this rod as well. So at temperature 25 degrees centigrade, this rod will have resistance. So let's say that resistance is R0 at T0. And if we increase the temperature of the environment, the temperature of this rod will also increase. Let's say the temperature of the environment become 55 degrees centigrade from the 25 degrees centigrade. Now the temperature of this rod will not be remain R0, but it will be increased. So the increase in the resistance is given by RT in this case. So this resistance has increased. Now the change in resistance with this temperature is given by this. So here we have the change in resistance RT minus R0. RT is higher than R0, therefore I write this RT minus R0. And in this case, this RT minus R0 is associated with the change in temperature. So here if I increase the temperature more, so then this RT minus R0 value will also high. So here this RT minus R0 is directly proportional to del T. Here in this case, this del T is given by this del T is actually T at degree centigrade minus T0. So this is the del T, and let's call this expression as equation 1. And similarly, we have the same copper rod. So this is, we have the copper rod, and this is that same copper rod. And let's consider now the temperature of this copper rod is considered to be let's say 30 degrees centigrade. And at this 30 degrees centigrade, let's the what we can say, the resistance R0 of this wire of this copper rod is considered roughly is to be 300 ohm. And similarly, the same rod with the same length and area I have considered here, and now only the temperature I have increased up to 35 degrees centigrade, and in this the R0 in this case is about 400 ohm. Now if I increase the temperature of this rod by 1 degree, so here if I increase the temperature by 1 degree, so T now become from 30 degrees centigrade to 31 degrees centigrade, 31 degrees centigrade. So in this case, this R0 will also increase. So that increase R0 is due to this temperature is given by RT. In this case, it may become let's say it increase to 305 ohm. Now at the same amount, if I increase the temperature from 35 to 36, this increasement is only 1 degree, just like this. But in this case, this RT will not increase by the same amount as increase here by from 300 ohm to 305. So in this case, it will not is 405. It will be more than that. So it will be 40 let's say 7. Why this not same? This because already the original temperature of this rod has increased, and by increasing the 1 degree rise, now the resistance of this will not be increased by the same amount as decrease here, because the overall temperature of these two rods are different. The internal energy of these two rods are different. The oscillation and the vibration motion of the atoms of the copper rod present present inside this rod is different. So therefore, by increasing only 1 degree, the overall effect on this copper will be different. Therefore, by increasing this by 1 degree, this the change in R0 and RT will be do not be same. So from here we can conclude that RT minus R0 mean the change in resistance is directly proportional to R0. So if the rod have already increased the R0 value, then the increase in that resistance will be more as compared to the rod will have initially the less ohm, the less what we can say, the less resistance. So here this rod will initially have the less resistance. Therefore, the increase in this resistance is less as compared to this rod. So from here I conclude this. So this let's call equation 2. So combine equation 1 and 2. Let's say I am taking partition here. Okay. Now combine equation 1 and 2. Combine equation 1 and 2. So it implies that RT minus R0 is directly proportional to del T R0. So instead of this proportionality sign, we will write, so we go to here, RT minus R0. Instead of that proportionality sign, we will put equality and the constant, and del T and R0 come in its own position here. Now instead of this constant, we will put the alpha value, alpha. So RT minus R0 is equal to alpha del T R0. Here this alpha is actually the called the what we can say, so let's this is called the coefficient of resistance. Now this is equation 3. So this become equation 3, and from equation 3 we can determine alpha as RT minus R0 divided by del T R0, and let's call this equation 4. So this is equation 4. Now we can this alpha is called the coefficient of resistance here. So this is the relation, equation 4 for the relation for the coefficient of resistance. Now we can generalize this relation to the coefficient of resistivity as. So in order to generalize this to coefficient of resistivity, we have to take the equation 3. Equation 3 implies here that RT minus R0 is equal to alpha del T R0, and multiply A by L on both sides of equation 3. A by L and let's RT minus R0, and similarly A divided by L, A by L alpha del T R0. So this is equation 4. Now similarly we know that the expression for the resistance is given by rho, so resistance is given by rho L by A, and from here we know that rho is equal to R A by L. So according to this, the equation 4 implies that. So here equation 4 implies that Ra by L. So here is Ra by L. In this case, R is del R. So this become del rho. This left side of the equation 4 become del rho, because del rho is given as Ra by L, and here is also Ra by L is equal to, we take this alpha, and the rest is del T here, del T, and now R naught A by L. So R naught A by L is equal to rho naught. So from here we can determine alpha is equal to, so from here the alpha is given by this, alpha is equal to del rho divided by del T rho naught. So this is equation 5, and this is actually, this equation 5 is the coefficient, the temperature coefficient of resistivity. This is the temperature coefficient of resistivity, which implies that the change in resistivity per degree rise in temperature per the original resistivity. Here is the temperature coefficient of resistance defined as the change in resistance per degree rise in temperature per the original resistance, because the change in resistance depend upon the change in temperature, and it also depend upon the original resistance as well. So therefore this is this resistivity focus on these two natural phenomenon of this material which is occurs. So here we find the temperature coefficient of resistance and resistivity. Now we will explore that this alpha, temperature coefficient of resistivity, may be positive, this may be positive, and this alpha may be negative. This positive temperature coefficient of resistivity is associated with the metals. So because the resistivity of the metal is increased by increasing the temperature of the metal, so therefore we call that positive temperature coefficient. The phenomenon occur inside the atoms of the metal metal or the conductor is the, as we know that the conductor have valence band, as we know that the conduction have valence bands, and that valence band is overlap on the conduction band. So there is the very less difference band gap between these. Therefore the valence, the electron always in the conduction band, and if we increase the temperature, the collision of that conduction electron with the atoms or the other free electron will be more, and therefore we can say that their resistivity will be more. And similarly the second type of the resistivity is the negative temperature coefficient of the resistivity is given, which is called by NTC, and this NTC is present in the insulator and the semiconductor. The electrons in the atoms of the insulator are tightly bound, so that electron do not take part in the conduction. When we increase the temperature, so the electrons are tightly bound, and if we increase the temperature, the tightly bound electrons will get the energy from the temperature, and due to which it can free from the atom, and that free electron is called conduction electron or free and due to which the current will flow in the conductor, and due to which the resistivity will be decreased. insulator have negative temperature coefficient because their resistivity is decreased with increasing temperature. And similarly, the resistivity of the semiconductor also decrease with increasing temperature, and the same phenomena occur here as well. The electrons are less tightly bound as compared to insulator, and more tightly bound as compared to the conduction, and by increasing the temperature of this semiconductor, that electron go to the conduction band and free from the atom, so therefore it involved in the conduction, and due to which the resistivity is decreased. So therefore the insulator and semiconductor have negative temperature coefficient, and the what we can say, the conductor have positive temperature coefficient. And that's it, guys. Thanks for watching.